visual cue effects on a classification accuracy estimation task in Immersive Scatterplots. This video gives you a brief overview about our TVCG paper. There are many interesting perception problems for VR visualization, and we picked visual cues because we believe visual cues can be very important. But the current VR applications use visual cues arbitrarily. For example, the sphere was rendered using ambient, diffuse, and specular channels, while the specular channel feels very unnecessary. Also, this shadow feels unnecessary and occludes the small bars near the tall bars, which may cause perceptual difficulties. Literature from perceptual psychology suggests that visual cues can strongly affect our perception, and the examples here show how texture and shading affect our perception of shape. However, perceptual psychology often focuses on a handful of visual elements like two spheres, or sometimes even just one. In visualizations, we may have thousands of visual elements where visual cues may display very different effects on our perception. Therefore, in this paper, we hope to encourage a systematic usage of VR visualizations and to understand the effect of visual cues on a task performance. And last, we hope to explore analytic tasks that can be supported by VR visualizations. Therefore, we used a task where we ask participants to estimate classification accuracy from an artificial neural network's last hidden layer output. And I will demonstrate that this task is feasible by showing an example of how the last hidden layer output gradually changes with accuracy in a training process. As we train the neural network, the classification accuracy increases, and the clusters in the last hidden layer outputs became more and more salient. Classification accuracy reflects the neural network's performance. Therefore, this task essentially asks participants to agree on the neural network's performance. It is a multi-class perception problem and takes a bit of thinking, and this task happens when the model designers try to identify misclassified instances to improve or debug a neural network model. To support this task, we first considered different devices. We used a desktop plus a monitor as the baseline. For our goals of improving VR applications, we used a VR head-mounted display. And the first visual cue we considered is visual motion, which can strongly affect depth perception. We have both static and dynamic conditions. In static conditions, participants saw a fixed graph. In dynamic conditions, participants can interact with the scatter plot. I record demos for the dynamic conditions on the desktop and in VR. Here we show how participants can interact with a scatter plot on the desktop. They can use the mouse to rotate a scatter plot around its center. They can also use the keyboard to navigate the scene. In VR, besides that the participants can rotate a scatter plot using the VR controller, they can also walk in the room to see the scatter plot from the different perspectives. The second visual cue we consider is shading. We test flat shading, simple shading, and ambient occlusion. Each adds more visual properties to the scatter plot. We also consider graphic projection, including both orthographic projection and perspective projection. The difference is that in perspective projection, the further spheres are smaller, and size is used as a depth cue. The last visual cue we considered is dimensionality. We projected the high-dimensional last hidden layer outputs to a 2D or a 3D space. Note that the top and bottom are the projections of the same dataset. Finally, we consider different data models. Because the shape of clusters and the number of data points both can affect participants' perception, Therefore, we used a text dataset plus a memory network and an image dataset plus a residual network to generate 2 sets of hidden layer outputs. To summarize, we manipulate 6 variables, including 4 visual cues. These 6 variables result in 52 validated combinations as our experimental conditions. In the experiment, we assigned 26 to each participant. In each condition, participants repeated 4 trials, and we recruited 32 participants who have prior experience with machine learning. To quantify participants' performance, we recorded 2 measures. We recorded error magnitude, defined as the amount of difference between participants' estimation and the actual classification accuracy. We also recorded response time, defined as the time between when the scatterplot was shown and then removed. We used Bayesian multi-level modeling to estimate the effects of the 6 variables, and we built a model for each measure. Next, we have a list of questions to guide our results and analysis. First, since we have 6 variables, we asked how does each variable affect participants' performance. We extract coefficients of the fixed effects and show their posteriores. There are many interesting observations here. We only indicated one strong effect. We found that visual motion can largely decrease error magnitude but increase response time. Next, because we have many variables, we are curious about the interaction effects between them. We found that there is an interaction effect between device and shading. This means that different shading levels affect response time differently depending on the device being used. Last, we closely look at 52 experimental conditions, or say 52 different scatterplot designs. We extract their posteriores and then use the medians to plot this figure. It visually summarizes all the effects. For example, for image dataset and static conditions, we found that adding shading progressively decreases error magnitude. However, for the same image dataset and dynamic conditions, we found that on a head-mounted display, adding shading increases error magnitude. For response time, we found that adding shading consistently increases response time. To summarize and conclude this work, we assessed the effect of visual cues on 2 different devices for 2 different datasets. We found strong effects from factors like visual motion. We also found small effects from factors like shading. Last, we suggest that the future work should use simple shading, but focus more on designing effective interaction techniques to leverage visual motion. And thank you so much for listening.